Hello students, welcome to BTech first year bridge course. In the last lecture, I have discussed about Biot-Savart law and the physical significance of divergence of magnetic field, right? Now today, in this lecture, I will discuss about curl of magnetic field and from there Ampere's circuital law. Okay, so let's start. We know that according to Biot-Savart law, the magnetic field at any point P due to a volume distribution of current is like this. Here R is the vector from the volume current element to the point of observation P. So here this is called source point and the P point where the magnetic field will be calculated is called field point and O is the origin. Okay, and here mu naught is called free space permeability. Now here you should note that the magnetic field is function of field point coordinates. The volume element dV is a function of source point coordinates and R is combination of source point and field point coordinates. Okay. Now since the gradient of 1 by R is actually minus of R vector by R cube, the magnetic field can be written like this. Here it is important to mention that the del operation is with respect to field point coordinates and the integration is over source point coordinates. Now we have to evaluate this J cross gradient 1 by R. Okay. So for that we have to use this vector identity. Curl of J vector by R is 1 by R curl J plus gradient 1 by R cross J. Now since the current density J is function of source point coordinate and del operation is with respect to field point coordinate, curl of J will be 0, right? And we have this term gradient 1 by R cross J. And after changing the sequence of these vectors, we get minus J cross gradient 1 by R. So using this relation, this form of magnetic field can be written like this. Now here you should note that we have pulled out the del cross operator. So this is allowed because del operation is with respect to field point coordinates and the integration is over source point coordinates. Now if we take curl on both sides and using this vector identity of curl A is equal to del dot A minus del square A, we get this form of curl of magnetic field. Now here this volume integration J by R is considered as this A in this vector identity. Okay. Now since the current density is with respect to source point coordinate and del operation is with respect to field point coordinate, del dot J here and del square J here will be 0 and we have these terms. Okay. Now let's simplify these two terms. At first let's focus on del square 1 by R term. Here capital R vector is actually small r vector minus small r prime vector. Now at r equals to r prime, 1 by r term becomes infinite. It has very large value at that point. So del square 1 by r can be considered as Dirac delta function. Now what is a Dirac delta function? So you know we have already introduced the concept of Dirac delta function in electrostatics in the discussion of divergence of electric field, right? Now you know that the electric field for a point charge at any point of r distance from the charge varies as 1 by r square, and if you operate divergence on 1 by r square, it will produce Dirac delta function, right? This occurs because this type of function has singularity at r equal to 0. It blows up at r equal to 0. Similarly, here also del square 1 by r is actually producing Dirac delta function. Okay. So basically one should tell this function is a distribution function, right? Now you can see that the function has infinitely large value at r equal to r prime, and at other points it is 0, and the area under this curve is 1. Okay. Now we have to use another fact that gradient 1 by r with respect to field point coordinates is opposite in direction but same in magnitude as the gradient of 1 by r with respect to source point coordinate. Now this you can think as taking derivative of any function with respect to field point coordinate, and it is same in magnitude of taking derivative of that function with respect to source point coordinate, and the direction will be opposite, right? So once you are taking derivative from the field point end, in other case you are taking derivative from source point end. Okay, and we get this form. Now let's further simplify it. So here we can write j dot grad prime 1 by r equals del prime dot j by r minus 1 by r del prime dot j, and here j is function of r prime, right, and dv is also function of source point coordinate, and this is delta function which is 0 other than at r prime equals to r point. So after integration the current density becomes function of r coordinate. Okay. Now as we are dealing with steady currents here, del prime dot j is 0, otherwise del prime dot j will be minus del rho del t. So what it means? So in general, if the charge density changes with time, then del dot j will be equals to minus of time rate of change of charge density in a particular region. This is actually called continuity equation. Okay. Now I am not discussing this continuity equation here. This will be discussed in details later on in main course when we will discuss Maxwell's equation in electromagnetic theory. Okay. Now coming back here, so curl of magnetic field becomes like this. Then using Gauss's divergence theorem, we can obtain this form. Here J is the current density of this volume distribution of current, and S is a closed surface which encloses a volume V within this current distribution. Now you know it is the volume that appears in the Biot-Savart law, right? And it can be large enough to include all the currents. Okay. Now we can make it bigger than that if we like, and basically if we do so, it will simplify the form of curl of magnetic field. Now this is permissible because the current density J is 0 out there anyway. So it will add nothing to this integral, right? Now the essential point is that on the boundary of this surface the current is 0. All currents are safely inside this surface. Okay, and hence the surface integral vanishes and we are left with this term. So we get curl of magnetic field is mu 0 times the current density J, and this is called differential form of Ampere's law. Now we have to remember this law is valid for magnetic field of steady currents, and in general it requires modification if current changes with time. Now this differential form can be converted into integral form by applying Stokes theorem. Now according to this theorem, the line integral of the magnetic field around a closed path C, which actually covers the point where the magnetic field will be calculated, that is equal to open surface integration of curl of magnetic field. So closed line integration of magnetic field is actually equal to the open surface integration of curl of magnetic field. So this is the Stokes theorem. Now here the open surface S is enclosed by this contour C. Now this will be equal to the mu 0 times to this open surface integration J dot ds, and this actually equal to the current passing through this surface, which we call as INC or I enclosed, and this is the current enclosed by this closed loop, and this closed loop is actually called Amperean loop. Okay, so the statement of the Ampere's law is the line integral of the magnetic field around any closed path is equal to mu 0 times the total current enclosed by the closed path. Now in this equation, the direction of integration around the contour C is associated with the direction of a positive current through this right hand thumb rule or right hand screw rule. Okay, so what is that? If a right hand screw is rotated in the direction of integration, then its direction of movement defines a positive current, and the current having opposite direction is considered to be negative. Okay, so what is the importance of this Ampere's circuital law? So it basically allows us to determine magnetic field in a very simple way for currents having special symmetry, where it is possible to find a closed path over which magnetic field is constant in magnitude. Okay, for example, here for a long straight current carrying wire, to find out the magnetic field at different outside points, we have to draw concentric circles of different radius through those points where we want to find out the magnetic field. Okay, these circles are called Amperean loops. So here we have symmetry in the system. Okay, and that is the magnitude of the magnetic field will be same all over the circular path, right? and the direction of the magnetic field will be tangential to the every point of the circle or this circular path. Okay, so this is all about Ampere's circuital law. Now today I am ending here. In the next lecture I will discuss about magnetic potential. Okay, thank you.